630. It's right opposite the mechanical engineering office. It's somewhere in that corridor. Starts at 6:30, ends at 7:30. And this is, I might go through some more changes. There are 10 questions, short answers. Absolutely, if you have read the notes and if you have followed my lectures and made some points or you followed what it is, you should have no problem in answering the midterm. So there are 10 questions. Total marks is 50. Total time is 60 minutes. The 10 may become 9. I don't know. But it will not increase. Okay. So that's about tomorrow's midterm. Now, regarding the lab BO1 and BO2, according to Trevor, presumably the problem is not with the software. It is with the hard disk or storage of the server. So they have changed it over the weekend. There are a lot of people who are involved from IT. In fact, I played badminton yesterday with one of them who was involved, and he told me it was that they had to change the hard disk. Not enough memory. Too many programs being launched. So, according to Trevor, everything is working, and I actually met him yesterday morning, and he showed it to me in his office how all the options work. And I sent an email last night. This is the second one. The first one I got only 4 people to respond. So please watch, look for your email. That's the only way I can communicate with you. So the second one that was sent last night need an update of whether you're able to access or not. So according to Trevor, nobody needs to come to the lab to access the software. This is my plan, current plan today. I will run it because BO1 has 10 people. I can't put 10 computers. I have only 6 in the lab. So that option doesn't really jive. Some people have to stay remote. But if all 10 can stay remote access, I will conduct the web as usual. This is what I'm planning. As you are ready to machine the lamp base, I may bring you into the lab to watch your part being machined. That nothing like seeing it live. And if you have to make any changes, yes, you can go back. And the final machining that's going to be done on HTP is the crucial or critical test, where that mating and fitting and all those, you can see it yourself. So I am keeping that option open, that when your part is being machined, you are going to be invited to come and see it yourself, rather than watch it remotely on a video. Okay, so that's my 1 cent worth speech. And I'm sure you probably are aware of the UMFA, University of Manitoba Faculty Association's strike quota that took place for 3 days, and their results have now come. Those of you who have not seen it, 85% have voted in favor. That doesn't mean the strike is going to take place. That means they are going to start talking, I guess, from tomorrow onwards. And if a settlement is reached, there would not be any strike. Nobody wants a strike. Okay? But I have to tell you that there are certain things that are absolutely wrong from the university perspective. Okay? So something must be done. Okay, that's Now I want to share my PowerPoint. Okay, I will go through this route. Okay. Okay. Are you able to see my revised screen? I want to move this out.
Yeah, we can see.
Okay. So we started this second case study in the PLC area. So let me take the picture. That will be a lot easier. Just to give you a quick revision. So the problem is we have a hydraulic actuator which is going to press on the part, and my pen went on the floor. Okay, so this is the actuation cylinder. This is the piston that comes down. So it comes down like this and returns back. So assume there is some spring inside for now. Real press doesn't work with the spring. The hydraulic fluid changes the direction. So you have a home switch, you have an advanced switch. Okay, and this is your part. So when this is actuated, this comes down and presses on the part or whatever. Maybe this is a sheet metal and forms it to whatever it should be. So there is, let's say this is a die and this is your part. Okay, so limit switch 1, limit switch 2, or sensor 1, sensor 2 to tell you home or advanced. 1, 2, 3, panic or safety curtain. Trigger switches. If you cross any one of these, the press should immediately stop. So we have taken the minimum number of inputs and outputs, and I explained how it can become very complicated. Now, something that is very critical to understand. What happens if the piston has advanced to this stage from the home? It is going down towards the part. This switch from 1 will become a 0. How about this switch? Will be a 0 and will continue to be a 0 until this piston comes all the way down. So there is a period in between when both switches will be not true or a 0. Okay? So if you design a logic on the basis that if it is home and if there is a part and if a start button is pressed, advance. The moment it leaves the home position, the logic is going to fail. So the pass press will immediately go back. It won't even go towards the part. Okay, so that's not good. The piston will work like a vibrating device, going up and down, but not really going towards its destination. So this should be taken care of in the logic. The other one that is important is to understand this switch G, go button. If you typically take the wall switch in your house, there are only two positions, an on and an off. Okay, so it remains in the position where it is pushed, either on or off, up or down, and it stays there. In the real industrial system, that's not the way it works. Okay, so the industrial systems work like this. Instead of a lever, there may be a push button, a red and a green, usually. So let's assume we are taking only one switch for now. If I go and press on this switch and hold my hand, it becomes 1. Then when I release my hand, let's assume there is a spring underneath which pushes the switch to neutral state, which is 0. So these type of switches are called momentary on. And in another terminology, they are also called toggle. Okay, toggle has a different meaning. Toggle is, it is always, there are 2 positions to the switch. No, 3 positions. One is up, another is down, and then center. Okay, the default position is center. So if you press the switch up and hold it, it'll remain in the up position. When once you release your hand, boom, it'll go back to the center position. Same thing will happen with the down switch. This is used in logic, process control, for a different type of application. Now the switch I am talking about in this case study belongs to this category. The on switch stays on only if you keep your hand on. Then it bounces back. And if it bounces back, you cannot cut the power to the RAM actuator. You should still sustain. Your logic should still sustain. Okay, so keep that in mind. That's an important assumption. Okay, so on this slide it says press sustains the power to the punch or the RAM during the downward stroke until sensor advance is deflected or sensed to be true. Okay. Now, in the real world, when it reaches the advanced position, you don't want to bounce back right away. You want to put a tiny little time delay. Okay. The time delay could be 1 second or some milliseconds or nanoseconds, depending on how much time is needed to make sure the part is fully stressed or to be on top of the die. But we are not using that timer at all. We are assuming that when the advanced switch reaches its advanced limit, done, bounce back instantaneously. Okay, so when it goes back, it does not require a power to take it home. This is where I said assume the spring pulls it back home. So typically you will remove the power to the RAM for a return stroke. So the power to the RAM is applied only in the downward stroke and is removed during the return stroke. These are assumptions for this problem, and the logic will take care of or will consider only these assumptions. If any of the assumption changes, the logic I'm going to show you is no longer going to be working for you. Okay, so this is the reason why it's very critical to make assumptions if you're responsible for making those assumptions, or if the designer of the system has made assumptions, you must adhere to those assumptions unless you want to question them. Okay, so let's go to the next slide. Is there one more? No. So let's identify the inputs and output variables for this process. Start button G equal to 1 when pressed, equal to 0 when released. Stop button. So in the start button case, the default position is 0, released. Only when you press it becomes 1, and it stays only when you hold it with your hand. Stop button, there is actually no stop button. It's actually the panic buttons, the 3 safety switches. They are normally 0. When you interrupt, it becomes 1. Now, I can introduce one more input, start button and a stop button. That means a G1 and a G2. To remove, for this case study, too many complications to start with, I'm not putting that in. Then the limit switch or the sensors to tell you advance and home, L1, L2. Then the actuation of the ram or the cylinder. Okay, let's assume A star. Okay, or A is one of them is input, the other one is the feedback. The input is the feedback when it's actually actuated, and the other one is the actual output. And these two states are shown as equal to 1 when it is actuating and equal to 0 when it is released. Go down. So 7 inputs, 2 power 7 is 128. So simply you may have to, if brute force, you have to run 128 row truth table starting from 1, 2, 3, 4, 5, 6, 7, all the way the 128th row. 1, 2, 3, 4, 5, 6, 7. Small letters. So all this, including this and this, will have an output that you, the designer, will decide. If there are more than one output, you have to analyze each one of those outputs. Okay? As I said in my last lecture, this is where I was. We are going to now segment the problem, not consider 128 rows. So the first thing I'm going to do is to take the 3 panic S1, S2, S3 and come up with one single output that represents what might happen if one of these inputs is going to be true or not true. So draw a truth table. You're dealing with the S1, S2, S3 and a single output S. So 2 power 3, 8 rows, and the input will have 8 rows as is shown on the diagram, and the output also will have 8 entries. And as I said in my last class, you have a single candidate with a 0 and 7 candidates with 1s. Logic can be done for both. So brute force, following previous examples. If row 2 or row 3 or row 4 or row 5 or row 6 or row 7 or row 8 is true, then output S is true. That means you are going to have a huge logic equation. Or we can say if not S1 and not S2 and not S3, output is not S. Logic is correct. So path of minimum execution, first row wins. So we are only going to consider the first row. So from truth table, not S equals not S1 and not S2 and not S3. Okay? De Morgan's law will allow you to simplify in a different form. In this case, the simplification from truth table is straightforward and simple. In order to come up with hardware, sometimes you will take this, which is exactly reflective of what comes from the truth table. So De Morgan's law tells you S is true if S1 or S2 or S3 is true, or, okay, which is correct. If any one of the safety switch is interrupted, S should be true, which is an alarm as an input going to the next stage, right? So what did we do up to this point? We took 3 inputs and reduced it to a single output. That means that 3 inputs does not have to be considered anymore as single inputs each. So out of 2 power 7 rows. Now you have dropped it 2 power 7 minus 2 power 3. Okay? So the problem is getting a little bit more manageable. Okay? Instead of 7 inputs, which is 128 rows. First stage, you dealt with only 3 inputs or 8 rows. Now let's go to the next stage. Create another truth table, okay, with an intermediate variable R, which tells you if the machine is running or not running, equal to 1 or a 0. Okay, and then an R prime to tell you that there is an output R prime which is going to come in as an input or a feedback. Okay, so construct another truth table with a G, which is the go button, S, which is the summed state of the panic, and processes running R, and an R prime. Another 3 input truth table with one single output R prime coming in. So G is the start, S is the panic, and R is the process. Candidates, again, caution. This is my solution to the problem and is based on what I decided R prime or when R prime should be true. If you think my assumption is wrong or any of the designer's assumption is wrong, you should come up with modifications. But if the designer was right in the first place, his or her solution will work and your solution is not going to work. Okay? So in PLC logic, like this is true of everything that I am doing in this course, well, we don't have to go to the machining at all. We can stay with simulation, say, everything is good. Everybody will say everybody's solution is good. Well, in the case of machining, some of you might have watched some things are not right, sequence is not right, which you did not capture, even though if you paid attention or anybody pays attention to the simulation, you might be catching the basic problems, not all. Okay, so through of the PLC labs, you are going to produce a solution, you are going to produce a program, you are going to implement it, and you're going to see it. If it doesn't work, then you go and fix it, right? So in this case, I have 3 ones and 5 zeros. Obviously, I'm going to take the least path and say if row 2 or row 5 or row 6 is true, R prime is true. Okay, so write the equation. Again, I have already said this. S is a summed representation of S1, S2, S3. So it comes in as a single input. So 3 rows, write the equation. R prime is row 2 or row 5 or row 6. And I'm not going to read except the first one. R prime is true when not G and not S and R, which represents row 2, and then a logical operation OR. That means either this or this or this. Row 5 is G and not S and not R. Then another OR. R is G and not S and an R. That comes from the truth table. Can it be simplified a little bit more? Again, these are very simple problems. So the reduction in terms of number of terms and the equation complexity is not going to be that big a deal. Okay, but hello? Am I getting a beep from somebody? I guess not. Is my audio clear?
I can hear you.
Yeah. Okay.
It's clear.
I can hear you.
Okay, I made some changes to my microphone and my laptop settings, so I'm just watching whether it's going to do the usual dropping down on audio or whatever. So far, it's good. Okay, so row 2 or row 5 or row 6 from truth table is the equation. Use distributive law, and the second state is shown, and in the second state, you have grouped this, which becomes a 1. So inclusion theorem, followed by characteristic theorem, followed by commutative and distributive law, and finally the reflective theorem reduces to this. So where is this and where is this? Which is simpler? Obviously the last step. So R prime, the output must be registered when S naught, which is no panic, and the process is running, or the go button is pressed. Now, it is very critical to understand what's inside this. This is very obvious. Well, there is no panic. Keep the process running. If it is running, keep the process running. But what is happening here? Why are R, letter R, and a logic operator R, and a G? What is it doing? Okay, this is where the assumption I made, the G, the go button, stays on only when your hand pressure is on the switch. It's a spring-loaded switch. So you want to start the process, you want to get this R prime going, you're going to check that there is no panic, and you're going to press the button. Okay, process R prime, output will come. Then this, when you release from 1 and it becomes a 0, this will go from a 0 to a 1. Yeah. No. I don't want to delete anything. This will go Hey. Keep. Okay. So this will go from a 0 to a 1. Crap. I have to get the pen going again. And somewhere here is the icon from the pen. It seems to have disappeared. Okay, doesn't matter. So it is critical that the status of R, our status of R and the G is captured, and it is captured in this equation. Keep it. Did we consider everything? No. There is a switch advanced and a switch home, L1, L2, which has not even come into the picture. So what we have done, 7 inputs was dropped to 4, but it got the S as an input from the previous stage. So 4 plus 1 became 5. And then you introduced another variable, or I have introduced an R and an R prime. So it went back to 6, right? Well, we can proceed by the gradual elimination of combination of input and output to go to the final stage. So what will now be actually only 4 inputs, but it is going to be joined by a few other inputs. So the next stage, we have the process feedback R prime, the switch at home L1, and the switch L2, which is advanced, and the RAM actuation A as a feedback, and the RAM actuation A prime as an output. Okay, so 4 inputs, 16 rows on the truth table, starting with 0, 0, 0, 0, going all the way to 1, 1, 1, 1, with all the possible combinations in between. Again, follow a disciplined route. There is nothing wrong in going helter-skelter, 0, 0, 0, 0, followed by 1, 1, 1, 1, followed by 0, 1, 0, 0, followed by 1, 0, 0, 1. Can you imagine you correcting somebody else's solution with all these going helter-skelter? But the answer is wrong, and you have to spend a lot of time in sieving through their solution to find out whether there are duplications that has eliminated some good possible candidates, or whether some output assumptions are wrong. So following a disciplined route, such as what is shown, where each state flips methodically, like R prime for the first 8 rows stays as 0, for the last 8 rows is becoming 1 as an input. L1, 4 rows, first 4 rows stays as 0, followed by 4 1s, followed by 4 zeros, and followed by 4 1s, and so on. And the last 2 rows as easy 0 0 0 1 1 0 1 1 is the possible states. So it gets duplicated 4 times. Okay, so my solution to the problem, or my logical thinking, has assigned row 10, row 13, and row 14 are the only possible state when the RAM should be actuated. So if I take row 10, If R prime, I should remove the word if. R prime and not L1 and not L2 and A, then generate A prime. Going to row 13, let me see whether my pen will bounce back. Okay, only my pen is working as a mouse. So what happened to it? It's somewhere hiding in the screen. I'm not going to waste my time again. Row 13, if, no, remove the word if. R prime and L1 and not L2 and not A, or A prime should be true. Row 14, R prime and L1 and not L2 and A, generate an output. So you have three candidates here. There's one more, which is the last row, this row. Row 10 or row 13 or row 14. Write the logical equations, which comes up in the next stage. Okay. Now, going back, how do you know whatever I put up on the truth table is correct? How would you examine that? Well, try and analyze using plain English language statements. R prime, that means process is running, and you are getting a feedback. L1 is not true. L2 is not true. Is that possible? And the actuation is true. As an input, it is getting a feedback. How is this possible? Well, this reflects the state when the RAM actuator has started coming down and has left the home position and has not reached the advanced position. So this row 10 will prevent the bouncing back and forth in the event you did not have other possible states. If you put only row 10, you'll keep oscillating. You'll try to go to the advanced position, then L1 is not true, boom, it'll come back and hit back. So it'll become yo-yo. Okay. Row 13. R prime is true. L1 is 1. That means it is home. L2 is 0. That it is not advanced. And A is 0. And you must make A prime 1. When does this happen? Well, it's the resting state. You came into the process. You want to get it going. So you press the go button. The previous analysis or the previous set of analysis got R prime going. And now row 13 will make the process go, will make the piston advance. How about row 14? 1, 1, 0, 1. R prime from the previous stage is true. L1 is home. L2 is not advanced. A is 1. That means you press the go button, everything is ready to go, and it starts moving. Okay. Now, I didn't put this up, or I didn't come to this truth table decision just like the flick of a button. It took some amount of time to arrive at this solution. And I can tell you, I'm not a superhuman, that every time I do a logic table, that it always ends up in the first attempt a correct solution. There is always some screw up here and there. So when you implement it, if it didn't work, you're going to go and examine your assumptions, which is something that's going to come up in your project 3 and 4. Okay, it's not going to be one straightforward implementation. Okay, so let's go to the next stage. What is the next stage? Though I have now explained to you by examining each row, so I don't want to go through it again. Establish the equations. Go to the apply the theorems. So I have a 1 sec. Okay, I skipped this. So from the truth table, A prime is row 10, row 13, row 14. And the equations that comes from them is shown as coming from the truth table. Distributive law would reduce it from 3 to 2 terms. Inclusion theorem will simplify it further to reduce into the 4th set of equation. Then characteristic theorem in combination with commutative law will result as 1, 2, 3, 4, 5th set of equations. And then using commutative law and reflective theorem, you will land up with A prime equals R prime and not L2, and within brackets either A or L1 being true. Now, this is not the final equation. You have to now bring in what you solved for the R prime in the previous tables and substitute back all of it into to form the final equation. So substituting for R prime, the equation shown at the top results. Now bring back S1, S2, S3 and replace the S with the actual inputs S1, S2, S3. So what you have in the second set of equation is more or less the final equation for this process. Is this the only solution? One thing that this course does to satisfy what the accreditation process dictates these days, as students must get involved in design. Not all courses, some courses, especially electives, that involve open-ended solution. That means if student A comes up with a solution which is correct, student B can come up with a solution which is a little bit different, but equally correct when it is implemented. It gives the same answer. C goes through a different route and comes up with the same answer, but in a different route. That's the open-ended nature of design problems. It's true in this case also. Like a lamp base, when you're going to come up with toolpath, I am sure there are going to be more than one variations in the way and more than one output coming out, but everybody will produce the lamp base, hopefully absolutely fitting, right? If everybody had the correct answer, but everybody may have a different machining time, different sequence, combination, right, of different tools, maybe not be using the same tools. That's the open-ended, and in PLC, similar stuff exists. Okay. What do they say? The proof of the pudding is in the eating. So you may come up with equations, but you have to implement on a model and verify that the model behaves exactly the way the process should behave, right? So we have only seen equations thus far. We have seen the truth table. So let me sum up. Statement of the problem, including the assumptions that you have been asked to make about the inputs and the outputs, resulting in putting together some problem logic statements, which goes to the next stage of drawing the truth table. If it is very manageable, 3 inputs or 4 inputs are easier, but anything beyond, you should start segmenting the problem, as was the case in this case. Called console lock example involved only 3 inputs, so there is no need to segment. Okay, truth table results in where the outputs that you decide should be true, and then you reduce them to logical equations by first coming up with the raw equations, considering all the rows, then putting together or including some theorems to reduce the problem, and finally coming up with a somewhat compact set of equations. If you really say, I don't care about all these logic equations, I'm going to take 7 inputs, I'm going to draw 128 rows, and I'm going to look at each row and come up with when they are true, and I'm going to write one wall full of equations. Absolutely correct, as long as your assumptions about the outputs are right on those 128 rows. But you will land up with some big mess in terms of equation. You will not compress, obviously. You decided to go through that route. And you will write very long equation. And you will, the last stage, which you have not seen, is to transfer them to computer amenable software-based equations that are going to be downloaded to the PLC. Just the way a part program from a drawing stage goes into the machine, PLC also don't understand all these equations that you have drawn, but you must convert the equations into a language that it understands. Okay, so that you have not seen, I will show you next stage. Now, I think that was the last slide on this set. Any questions before I move on to the next section? Anybody? Is everything clear? Obviously, yes. Okay. Those who were not there when we went through the student list, I don't think I covered everybody. There are 10 people in BO1 and 3 people in BO2. Some of you already said you're able to remotely link. Stay remotely linked. If all the 6 computers in the lab, which are ME Robo Lab 01 to 06, is going to be accessed by somebody else. Obviously, BO1, I have only 6 computers, and if there are 10 students, and if all want to access that computer, obviously some will be left out. Okay, so try and stay remotely with other sources that CEME and so on. And Trevor has suggested doing RDP, remote desktop protocol, or whatever that I have mentioned in my email. And I have told Trevor for this afternoon that I'm going to invite him as a standby for the lab session. In the event you have any questions about that remote access protocol, I will invite him. Otherwise, he will not be showing up. Okay. PO2 is not an issue at this stage because there are only 3 people. Okay. Outside of the lab time, you can access anything you want. 24 hours. Okay. You can go CMU virtual or the AutoCAD or the CAD lab or my lab, whatever that's available, make use of it. And as I said, it is not the software issue. It had something to do with the hard disk of the server that had to be upgraded. That's what I was told by the IAST people. So presumably they worked during the weekend. Okay, done. Let's close this section. Okay, let me go back. Okay, do you see my next slide coming from another set? It
Yeah.
would say, okay, good. Okay, this is already in G2L. I loaded it last night. Okay. In the PLC, I have 3 sections. You are now getting into the second section, and there is a third section. Now, upfront, let me ask, how many of you have already taken the ECE course, the core course, not the first year, at the 3rd and 4th year level? Anybody?
I haven't.
Okay, anybody who has taken the course?
Yes, I took it.
Okay, if I ask, oh, go ahead.
I've
Somebody
taken the
else?
course.
2. 2 out of 13. Is there anybody else?
Yeah, I've taken both the courses.
Okay, 3. Any more?
I took it.
4? 4 going closed. Okay, if I ask you, did you do or did they do Karna map? There's the word Karna map. Strike a bell.
No.
1 no. There are 3 more.
No, I don't think so.
Okay, 2 down. 3 and
Yeah,
4.
I don't think we did it
I don't
either.
recall any of that.
Okay. Karna map is an alternate to truth table using equations. So I would do that if you guys have not seen it at all. Obviously, 4 out of 13, 9 still remaining. Obviously, you're not going to see. The 9 remaining are also not going to see. When I used to be the head, I revised that ECE course and told them majority of what they are doing is absolutely useless for mechanicals. Okay, so I gave them the revised what should be taught. Obviously, not followed. Okay, so I did tell Dr. Kuhn that before I lay down my guard, I'll take over the ECE course and teach as to what mechanicals should know about ECE content. It hasn't happened yet because I am fully overwhelmed with whatever I'm doing. But I think that's what should be done. So I asked them to teach Karna map actually with the process implementation. Either they don't want to do it or they don't have the expertise to do it. Who knows? They should have the expertise to do the Karna map, but maybe not process model. So in the second section, so there is a third section coming up with Karna map and so on. But second section is going to take you through a different route of what the first section took, where we did everything using truth table. Is there another route without going through the truth table where you can logically think through the problem and come up with the solution? That's what is going to happen in your project 3 and 4. Project 3, you will go through the truth table analysis and reduce the equations and so on. And then you're going to proceed to the problem 4, bypassing the truth table because the problem is going to become a little bit more involved. Okay, so as it says up front, difficult to describe all industrial problems using truth table alone. It's a good start. Okay, because remember I said in the punch press problem, when you go to the advanced stage of pressing on the part, you don't instantaneously bounce back. There is a time delay. The time delay may be less than 1 second, but it is still a time delay. Okay, timers, not straightforward to use on a truth table because there are two possible states within an input itself, making it more complicated. Counters. Well, what are counters? If you are involved in a process where parts are being dumped one by one on a conveyor belt and being moved to the destination, what would be an example? Let's say you're involved in making cereals. The last stage is the cereals being filled in boxes and the box being sealed. Okay, and the sealed boxes keep moving at a rapid pace towards wherever it should be dispatched or taken out and packaged. Okay. Another example which you can relate to very easily, which is not a manufacturing process. At the airport, when the plane arrives and you wait at the carousel where your baggages are going to come after a time delay of 10 minutes, 5 minutes, or 1 hour, who knows? Usually there's not that much of a delay these days. So let's say 10 minutes, one by one the boxes are coming from somewhere else through secondary conveyors into the final destination, which is the carousel. Okay, now counters could be involved. If they know by computer 154 boxes should be checked out because sometimes multiple planes arrive, right? So they can start controlling the conveyor. Okay, once you reach the 154, shut it off until I restart again and start loading the next. All this happen behind the scene, I can tell you. Okay? Counters can also come into the play if I'm doing milk, filling milk in a 1 liter, a 2 liter, or a 4 liter jug, all coming out of the same process, but packaging is done by different machines. I can say next 100 and whatever, 50 plus is 1 liter. Stop the machine and switch over to the second machine. Now I want to give you 4-liter jugs. So it's a different process of handling, closing them or so on, where counters will start coming in very powerfully. Now timers and delays, they both represent time elements, but used in a different sense. Simple example of a delay is take your home heating system, especially the modern ones, the high efficiency furnace. There is a thermostat which tells you, well, you set it for 20, now it's going 19.95. So it's time to switch on the furnace. Nothing happens instantaneously in the high efficiency furnaces these days. A signal is sent to the controller, hey, start the furnace. So the first thing that it does is turns the heater on without the fan. That means your condenser is preheated for 3 seconds, 3 minutes, 2 minutes, whatever they set as the time. Because they want to make it very efficient. They don't want to blow cold air through the house before the condenser is warmed. So there is a delay or a timer that is causing the delay. Then similar process, when the temperature has reached the 20 or whatever that you set, the fan is not switched off first. The condenser heating is switched off so that you extract whatever that is there due to the previous continuous heating, extract every bit of energy out of it without wasting, and then shut it off. So these are all examples that I gave you in something that you can relate to, but I'll give you more examples as I go by from the actual process where the timers, counters, and delays come into play. Then you're also going to see introduction of internal outputs and latches. I would not explain them right now. I will do that in a later stage. But internal outputs and latches are going to pose some challenge in incorporating into the truth table. Okay, so problems from simple to complex problems can be analyzed using truth table as a starter or another route. So what we are going to introduce is logic network diagrams. Okay, what are logic network diagrams? Well, take a ladder that you use to climb. There is a left rail and a right rail, the two support structures on which your steps are kind of fixed to. Now, if you consider the left rail as a supply voltage hot with respect to neutral, which is on the right hand side, which is the right rail. And if you consider all these steps as some resistors that are allowing conduction from the left rail with respect to the ground, which is the right rail, through the resistors, you have a network of resistors that are, each resistor may be bulbs. For lack of a more complex example, bulbs are simple. So let's say you have a 60 watt or a 40 watt or a 30 watt or all are 60 watt, but you have multiple bulbs. So this represents something that you would consider as a parallel operation. Okay, so you've only got two levels of voltages, high on the left, which is true, and low on the right side, which is false. Okay, true or false. So the logic network diagram for the console lock. Did I miss a slide? Just a minute. Okay, no, I didn't miss a slide. Remember the equation that came out? No, I would not expect you to remember. Oh, that reminds me. You do not have to read the PLC first section. For the test, only the CNC is there. Yeah. So, the logic network diagram for the console lock example is represented here, but what does it mean? I did draw this using hardware diagram, but now we are going to get into more of it. So the equation was P prime equals not L and P or S and L. So if you put it using standard logic gates, what you have at the top, what exactly happened to my pen? Where did it go? Okay, I am not going to waste my time in making it work now. Pen is here. Oh yes, it came back. I think. Okay, so I have an AND, I have an AND, I have an OR, I have a NOT. Each one is analog or whatever chip you want to call. So one NOT, two ANDs, and one OR. This is the equation. So L is supplied here. L comes here. Output is not L. Okay, that's the first input to the AND. P, so not L and P is this. That goes to this OR gate. So this is not LP. Okay, and then an S and an L, which is this. The output is the other input to the R. Either S and N, S and L, or L naught and P. One of them needs to be true to fire away P prime. Okay, so as I said before, if this is all you're going to do as process control automation, you're not going to lock up a $800 PLC to do this. Go and develop this equation. But in order to do this, you went through this process, or you have to go through this process to use the minimum number of the gates. If this is $5 of investment and you land up without compression $50 of investment, yeah, you're blowing 10 times the cost on each controller. So you got to make the analysis reduce the cost. Okay, so that's the simple example of a logic network diagram. Okay, analogy is series circuits are AND, parallel circuits are OR, either or OR. So if you take your Christmas lights that you might hang in your Christmas tree or outside in the house, it can be either wired as parallel bulbs. That means even if one bulb blows, the others will work. Or if it is put as series, if one goes, everything goes, right? So that's the simple example of AND and OR. Okay, now on the previous example, this is a 2-input AND. Okay, what happens if I had more coming in? Yes, logic gates are available for multiple inputs. Okay, as is shown here. Okay, either you cascade like this, inefficient way, or you replace it with this. Multiple input AND is available. Same way, if you want to do this operation, either you invest on this or you buy this. Okay, but if you invest on this, A, B, C, D, all the way up to whatever you have, 6 inputs have to be true. Whereas here, segmented, well, I don't care if this is not true. That means shut down the stage here. Okay, and I can cut everything off and put another set of equations or logic gates here and segment the problem, right? So there are pros and cons, but stuff is available. Okay, my cell telephone is going to ring in 1 minute. Oh, it's already started ringing. Okay, so I am going to close here. We'll continue on Thursday. And once again, let me remind you of the test tomorrow. And the test tomorrow is worth 10%. And the next test is also worth 10. So you get 20 out of the midterm tests. Okay, any questions before I close?
Could you remind me of the room that we're taking the test in again?
Yeah, it's on an email that I sent. It's room E3330,
Okay.
right opposite the mechanical engineering office, which is E3327. I made a mistake in my last lecture and said E3327. It's actually E3330. Okay.
And
6:30.
the test will just cover things we've covered in class so far, like different types of commissioning.
Whatever, if you read my PPT slides and if you substitute or argument with whatever you grasp from my lectures, you should have no problem in getting 100%.
Fantastic. Thank you.
I
Okay.
just wanted to confirm that you said the PLCs are not going to be covered,
No.
just CNC.
Yes, CNC.
Okay, thank you.
Okay. I'm
Are
going to
you
close. Yep.
are you gonna expect anything that's specific on the C core? I mean the PARC program.
You're not going to write part program, no.
No, okay.
But you should know what is in it.
Okay.
Okay. See you guys.